Hey guys, how you doing? It's Coach Scott. Got another couple of videos to go with periodic trends, periodic table. Let's talk about electronegativity. All right, let's talk about electronegativity. So what is electronegativity? Well, it's the ability of an atom to attract other electrons. All right, we talked about ionization energy, which is the ability of the atom to hold on to its electrons and the amount of energy is required to pull it. Electronegativity is a little bit opposite of that. It's trying to steal electrons. Bunch of thieves, right? So, using Coulomb's law, an atom with a higher Coulombic force or higher attractive force with its own electrons will also have a high attractive force with other electrons. So, let's think about boron, carbon, and nitrogen. Boron, carbon, and nitrogen. All right. So, boron, if we wrote that periodic, or if we wrote its Coulombic law out, it'd be force equal. Boron's got a zip of. Let me get my periodic table out, Phil. So boron would have a 3 K E squared over R squared. That'd be boron. And then we're comparing it to carbon. Carbon, of course, would be force equal 4 Ke squared over R squared. And then nitrogen would be force equals 5 Ke squared over R squared. All right. So nitrogen has a higher Coulombic force. So that means what? All right. So increasing force, boron would have less force. Let's see if we can do that. Oh, no, that just draws right there. So let me turn this off. All right. Grab us that. So let's see if we're right. Yes, boron would have less force holding on to its electrons than carbon, which would have less force than nitrogen. Now, if you think about it, how does electronegativity relate to ionization energy and atomic radius? So electronegativity will increase as ionization increases. All right, increases. Electronegativity also increases as atomic radius decreases. Inverse relationship. But if we know how it works according to Coulomb's law, we'll have a better understanding of it all. So as we go across a period, the Zeph increases, and the force between the nucleus and its electrons will also increase. And as this force increases, it's going to be easier for the atom to steal some other electrons. So that means electronegativity will increase. All right, so as we go across a period, like across that period, electronegativity increases. Okay, it increases. Now, as we go down a group, okay, we've got more energy levels, okay, that will increase the radius. Now, as the force between the nucleus and electrons is going to decrease because the R squared in the denominator will cause the force to decrease, and it makes it harder for the atoms to attract electrons. So as we go down a group, okay, down a group, all right, it's electronegativity decreases. So it becomes less. Higher, less. Okay? Yeah. So now we've got some exceptions. So we got our noble gases, right? Now those are some of the smallest atoms because of its force keeping those valence electrons in. But for the most part, we leave that out of the electronegativity trend because they're full. They don't really want electrons. they don't want to get rid of any because they're stable. All right. Why do you think that is? Well, I just answered it. Is because they are stable the way they are. They don't want to grab electrons. They don't want to give up any electrons. They just want to be themselves, right? They've got a full shell. They got a full energy level. So if they were to gain or lose an electron, they would lose their stability of a noble gas, right? So they don't really like them. They don't want them. They just are. All right. So here's some other exceptions. The transition metals, the intertransition metals, there's some weird trends in there. And why? Because when you're dealing with transition metals, you're talking about those inner d orbitals and the f orbitals. Remember, on period 4, row 4, there we're going, when we go to the transition metals, we're going to the d subshells. All right. So because they're inner, there's not as much of the shielding constant stuff going on. Okay, like the S's and the P's are the main group electrons. So these elements with the that have got a d or an f orbital, they're going to have weird atomic radii, and they're not really going to follow the trend per se. So I wouldn't worry too much about them when it comes to trends. All right, so let's talk about this. Let's talk about the electronegativity and the first ionization energy trends. All right, so going across a period, all right, going across from left to right across the period, electronegativity and ionization energy will increase. Why? Because the Zeph increases, and that causes the force of attraction between the nucleus and the valence electrons to strengthen. And it will take more energy to remove those electrons than what it's worth, right? All right, so let's see. Electronegativity and first ionization energy is going to decrease as you go down a group. Why? Because of the R squared. The size of the shells increase, right? And the distance between the nucleus and the outer, the valence electrons will also increase, which means what? The Coulombic force of attraction will decrease. So, we talked about the first ionization energy. Let's go into the additional ionization energies. It requires more energy to remove each successive electron. So if I remove the first electron from beryllium, it's going to be 1 ionization energy. Then it's got another electron at the beryllium cation. Then that's going to take the second ionization energy to remove the second electron to get it into the helium configuration. Then it will take the third ionization energy to remove that third electron, and then the fourth ionization energy to remove the hydrogen. All right. The second ionization energy will require more energy. Why? Because the Zeph has really increased. Now instead of a Zeph for the beryllium cation, instead of it being 2, it's going to be 1. There's going to be, 3 protons? 3, it's going to have 4 protons, 3 electrons, right? So there's a lot more force pulling those valence electrons, a lot more positive force. And for that second to the third ionization energy, it's going to take even more. There's 2 electrons left. There's 4 protons pulling it in. It's going to take a lot of energy to pull that out. So when all valence electrons have been removed, all right, all these right here and right there, then we're going to have a noble gas configuration, all right? And then it's going to take a lot of energy to remove that electron once it gets into its noble gas configuration. So once beryllium gives up its first, it's in group 2, its first electron, its second electron, now it's got a Be plus 2 cation. That means it's got 4 protons, it's got 2 electrons, all right? And if you remember that the helium has a 2 electron configuration, it will take a lot of energy to remove that third electron. It's just going to be a tremendous amount. So yeah, it can be done, but yeah, it's going to be done in a lab. All right. So we covered that. We covered the, what do we do? Electronegativity, the additional ionization energies. Let's go ahead and let's go into the metallic structure. All right, there's only a couple of slides on that. And then we'll be done with periodic trends. So now let's go into metallic character of our electrons. Okay, so let's think about some characteristics of a metal. And we know what metals are. We've played with them, so on and so forth. For a metal to conduct electricity or heat, and we know metals do, it's got to have electrons that are going to be free to move about and not tightly bound up to a particular atom. So the metallic character of an element is a measure of how loosely it holds on to its outer electrons. What are we going to be talking about? Oh, Coulomb's law. So if we look at the metallic character of an element, it's going to be inversely related to its electronegativity. All right, so metallic character will increase going that way. All right, and it's going to increase going down. Okay, it's going to decrease going that way. So these are your metals, and of course these are your, they have less metallic structure. We call them nonmetals. All right, so it'll increase. So what's the relationship between the first ionization energy, okay, and the metallic character? Well, it's going to be the same. It's going to have the inverse relationship. Whoops, hit the wrong button. All right, the greater the first ionization energy, the lower the metallic character. So it's going to be an inverse relationship also. All right, so that's how metallic character works. Those are the trends we're going to worry about. First ionization energy or ionization energy itself, electronegativity, atomic radius, and metallic character. Okay, guys, this is Coach Scott saying have a good evening. We will see you on the flip side. Deuces.